Hello everyone, this is my presentation for Stat 157 Bayesian Statistics at UC Berkeley. My name is Star, and today I will give a brief introduction to variational inference. Here's the agenda for the presentation. Firstly, I will present an overview and the problem context for variational inference. Then I will go over the detailed concepts and theories behind it. After that, I will use the univariate Gaussian model as an example to demonstrate application of VI. We will also compare the popular Markov-Chain Monte Carlo methods with variational inferences. I will finish the presentation talking about some of the open problems in academia regarding this topic. So it all begins with the very basic and fundamental concept that every Bayesian statistics course will touch upon. We know that lots of modern statistical inference problems under the Bayesian framework depends on the calculation of the posterior via the famous Bayes rule. It says that the posterior of the model parameters equals the likelihood of the data multiplied by the prior density of the parameters divided by the model evidence, which can be understood as the marginal probability of observing the data. By the way, in general, the theta here is a vector of parameters that are also called latent variables because we cannot directly observe them. I might use these terms interchangeably from now on. So it turns out that the evidence is tricky. In many cases, it is either intractable or difficult to calculate. So its formula involves an integral over the entire parameter space, assuming that we are having continuous latent variables. In the discrete probability space, we might have a summation instead of integration, but the issue it poses remains the same. So to solve this issue, we want to bypass calculating the evidence. So we know the evidence actually integrates out the parameters, and therefore it's just a function of the data point. As a result, the posterior is simply proportional to the product of our likelihood and the prior. So for certain combination of the likelihood and the prior, you can easily identify the distribution of the posterior density by pattern matching with some non-distributions. This is also why researchers love conjugate priors. If your problem happens to allow this type of solution, then you can get an exact posterior with no need for approximation. However, in most cases, the model is so complicated that the first solution might not work. We can actually further the above relationship and notice that the proportion of our posterior density evaluated at different values actually equals the proportion of the likelihoods based on these two values multiplied by the proportion of their prior densities. This equation is exact, and it tells us the relative density in the posterior. This actually becomes an important factor within the so-called acceptance probability in MCMC methods like Metropolis-Hastings algorithms. But we won't spend a lot of time talking about this in our presentation. So now it's now the time. Variational inference is actually the third solution to this problem. Its basic idea in a sentence is to turn the approximation problem into an optimization problem. So this is the optimization setup. Basically, the idea is to pick the distribution inside the variational family Q that minimizes the difference between this proposed model and the posterior density measured by a loss function L. This might sound complicated because we introduce this in two new concepts. The first is the variational family. So a variational family can be treated as a collection of all distributions that we want to search and optimize in. The complexity of which determines both the difficulty of the optimization and the accuracy of our best approximation, Q star. We will give a concrete example of a variational family in the following slides. For the second concept is a loss function. The idea is that we want to assess the similarities or the distances between two probability distributions. You might immediately see that the KL divergence is a good choice. And it is exactly what we are about to use here. But it's also worth noting that some alternative measures can be used as well in certain scenarios. So it's time for some theoretical details into variational inference. First, the KL divergence between P and Q is defined as the expectation of log Px minus the expectation of log Qx. So both expectations are taken over P. It is apparent that the KL divergence is not symmetric from this formulation, meaning that the KLPQ is usually not the same as the KLQP. So when we try to apply it to our variational inference optimization laws, we see that the KL divergence between a proposed density Q theta and a true posterior density equals to the expectation over log Q theta minus the expectation of the log posterior. So you might ask, can we calculate this quantity exactly? Unfortunately, the answer is no. As we further expand the second term, we see that it involves the log joint density and the log evidence. So the very reason we resort to variational inference is the difficulty calculating evidence. For the same reason, we cannot get an exact K-val divergence using this formula. However, here comes a trick. Let's define the evidence lower bound, ELBO, as the expectation of log joint minus the expectation of log Q theta, which by some algebra manipulation makes it equivalent to the log evidence subtracted by the KL divergence we want to minimize above. This also explains its name, because the KL divergence as a measure of distance is non-negative. So the ELBO is smaller or equal to the log evidence and serves as a lower bound. Most importantly, the task of minimizing KL divergence now becomes a task that maximizes the ELBO, since log evidence is fixed. So I just mentioned the first interesting intuition about KL divergence. The second interesting thing that we can get out of the ELBO is the following. There's actually another way to break down ELBO into the expectation of the log likelihood instead of evidence subtracted by another KL divergence. This time, it's the KL divergence between the proposed density and the prior. So to maximize the ELBO, we want to maximize the first term and minimize the second term on the right-hand side. And let's see what these requirements entail. Since the expectation is taken over Q, we can only optimize the first term if we place some density or mass of Q on regions where the log likelihood is high. The second term is even more straightforward. It says that we should make Q as similar as to the prior of the latent variables as possible if we want to minimize the second term. Bingo! We thus see the familiar likelihood prior trade-off in some Bayesian posterior estimators, and it's not surprising to get a similar result even if we are not doing the exact calculation. So now let's talk about variational families. There are many different choices, but for this presentation, we introduce a simple yet widely used one called the mean-field variational family. The assumption is that we have a vector of latent variables theta, which contains theta 1 to theta k, and the variational density for theta is the product of the individual densities for each variable. For this setup, there exists an easy way to optimize with the coordinate ascent variational inference algorithm, which we call CAVI. So the CAVI algorithm takes in a model and the dataset, or observation X. The goal is to output the variational density of the latent variables, which maximizes the ELBO and subsequently minimizes the KL divergence to the true posterior that we want to approximate. So we start with initializing the variational densities for the individual latent variable. We can do a random initialization. Because according to the mean field assumption, these factors are independent of each other. Next, we enter an iterative process. In the first part of the iteration, we want to set a variational density of the jth latent variable to be proportional to the exponential expected log joint density, where the expectation is taken over all other latent variables to ensure that on the right-hand side it is also just a function of theta j. We keep the other variational factors fixed when we update one of them. So after we finishing updating every individual latent variable, we can calculate the ELBO at the current variational density. whose formula has been mentioned before and be computed in closed form. We will stop the iteration when the ELBO converges, namely the ELBO from the last iteration is very close to the current one. So to derive and justify the CAVI algorithm, we simply need to notice that we can rewrite the ELBO for a single latent variable with iterative expectation and gathering all the terms irrelevant to Qj into a constant. The first two terms on the right-hand side actually equals the k-out divergence between the variational density for the jth latent variable and the exponential of expected log join density. In order to maximize the ELBO, we can simply just set the former to look like the latter. This is the derivation for the first step in the iteration process. Okay, so far we have covered the basic of variational inference, the mean field variational family, and the CAVI algorithm. Here's an example that demonstrates this idea in action. So in this univariate normal model, we have a bunch of one-dimensional data points, x, independently and identically sampled from a normal distribution with latent variables mu and sigma, the location and scale parameters. We put a normal prior on mu with mean mu 0 and variance sigma square. And the prior of sigma square follows an inverse gamma distribution with alpha 0 and beta 0 as the parameters. Now, according to the mean field variational family, we assume that the variational density for mu and sigma are independent, so we can optimize their variational density separately. And the ELBO is straightforward to calculate as well, which involves the joint likelihood, the priors, and the log Q for mu and sigma. So remember, the CAVI algorithm iteratively calculates the ELBO and updates the variational density for each latent variable until convergence. So we first try to update the mean, the mu. Recall the formula that we should set the variational density to be the exponential of expected log join density. We take log for both sides, so the calculation is simpler. We can also gather all the irrelevant components into a constant. So the first term in the expectation is simply the log likelihood. And since the model tells us that the data is IID normally distributed, we can easily express this quantity. We also shift the terms that do not depend on mu to the constant. And similarly, the log prior mu can be expressed in a similar manner because it is also normal. Now, putting things together, we can combine the terms inside the expectation. At this moment, we should realize that the optimal variational form of mu should be a normal distribution as well. This might not be too obvious in other more complicated examples, but we can simply complete a square for mu in this case and match the form. After some algebraic manipulation, we'll get this form on the right-hand side. And in order to maximize the ELBO, we set the variational density for mu to be a normal with new mean and variance. These are what we call the updates for our variational factors. And such iterative updates are the key to achieving better and better approximation to the true posterior. The takeaway here is that we are not doing approximation with sampling. Instead, at each update, we are moving to a local maximum for a single latent variable, holding the other ones constant. And we will do it for each of them until convergence. The other observation is that the updates for sigma n, which is the variance for mu, depends on the expectation of sigma square, which is taken over the variational density of sigma. So the different variational factors actually depend on each other in some cases. So similarly, we can also calculate the variational density of sigma, but this time we won't spend so much time on the calculation. The result is that the variational density for sigma also follows an inverse gamma distribution, the same as its prior, with the updated parameters alpha n and beta n, which we can explicitly calculate from the priors and from the data. This basically wraps up the specific derivation on the application of variational inference to this simple example. I borrowed and modified Susanna's code and run some experiment on it. So this is the visualization in the first iteration of the CAVI algorithm on the univariate normal model. The blue histogram is the plot corresponding to our data. The orange curve is the normal density, with its mean being the expected value of the variational density for mu, and its variance being the expected value for the variational density for sigma squared. So it is similar to a posterior predictive density based on Q. At the random initialization in this first iteration, we see that the histogram and the curve looks kind of different. But after we update and match the mean, we see that the orange curve shifts leftward and centers on the data mean, as we can expect. And after another iteration, we update and match the variances as well. Now the normal curve not only matches the scale, but also the mean of the data distribution. For this simple example, it takes only 3 iterations for ELBO to converge, and we obtain a very good approximation in the end. It might be harder for other cases, however. So after all this formula and calculations, it's time for some qualitative assessments. Here's a comparison chart between variational inference and the popular MCMC method. So in MCMC, we treat the problem as approximation with samples, but the core idea in variational inference is treat approximation as optimization. As a result, the computational speed of MCMC is slow generally, because we need to take lots of samples. But in VI, the iterative process we have seen is typically quick to converge. There is good asymptotic guarantee for MCMC, because we know that it's designed that the stationary distribution of its Markov chain is just a posterior. But in VI, we do not have such general guarantee. As a result of these differences, we also see different application scenarios. MCMC is really suitable for small data sets where precise posterior is really desirable. And researchers will apply VI to analyze huge data sets like text documents, image histograms that only requires general probabilistic model. So in the last part of the presentation, we'll look at some of the popular and open problems in this field. The first area of interest is to find alternative measures in the variational objective function. The KL divergence seems to be a natural choice, but researchers are also trying to borrow ideas from it. For example, in the expectation propagation algorithm proposed by Minka, they use a similar but different kind of a KL divergence. Some other works also focus on divergences that give us a tighter lower bounds than ELBO for better approximation. Secondly, we have been using the mean field variational density family in this example, but this family makes strong independence assumptions and fails to capture the covariances among the latent variables. To augment expressibility, researchers have tried to come up with other type of variational families. A famous example is the so-called structured variational inference proposed by Soar and Jordan, and there are also other types of alternatives here. Finally, we made a comparison of VI and MCMC in a previous slide. So it's also desirable to combine the efficiency of variational inference with the precision of MCMC. In one way, researchers used fitted variational densities as component for the proposal distribution for Metropolis Hastings algorithm. But on the other way, there are also methods that leverages Monte Carlo methods to evaluate the expectations that we see a lot inside the variational inference calculations. In addition to the references listed in the open problems before, here are other resources that helped me a lot in this presentation. And this is everything that I want to say. A lot of thanks for your listening.